Hello and welcome to the fifth episode in our series on information theory. Today we will talk about the fundamental theorem for a noiseless channel, also known as the source coding theorem, and we will introduce the concept of a channel capacity, as well as describe the ways of efficiently encoding information sent through our channel. Let's get back to our communication system and focus on the source and the channel. As you might remember from our previous episodes, our source can be described by its entropy. This tells us how much information it produces. The way that we can describe our channel is by its capacity C, which tells us how many bits we can send each second. It's given by this formula, in which T is the duration of our signals and N is the number of allowed signals of duration T. This essentially means that we calculate it by sending messages through our channel over and over again for a long time. Then we take the information content that we sent and divide it by the time it took, giving us information per second of our channel. What the fundamental theorem for a noiseless channel tells us is that we can send messages through our channel with a rate that's very close to the capacity of our channel divided by the entropy of our source. Epsilon here is just a very small number that indicates that the outcome is a little bit smaller than our fraction. Take a moment to think how beautiful and logical this outcome is. Remember that the capacity is how much information we can send in a second, and the entropy tells us how much information we expect from one symbol produced by our source. Divide them, and that gives us the number of symbols that we can send each second. To show you how important this theorem is, imagine this scenario. You are resting in a tavern and a man runs in, saying that they have a high-paying job at a local weather station. They have a channel that can send 2 bits a second, and they need someone to help them transmit weather data from one station to another. You can hear everyone around you saying, "Easy," and getting up to take the job. But the weatherman tells you a catch. There are 8 possible weather conditions, and we need to send 10,000 states in 10,000 seconds. Everyone quickly does the math in their heads and screams that it's not possible. One symbol requires 3 bits to encode, and the channel capacity is only 2 bits. But you know better. You approach the man and tell him that it might be possible to send that data. But first, you have to take a quick look at it and calculate its entropy. Going into the weather station, you notice that indeed, just as you expected, there are weather states that are much more probable than the other ones. So you quickly go over all of them and calculate the entropy to check how much information there really is in the set of possible weather conditions. You then use the outcome to calculate the possible rate at which you can send the information. And it turns out that it's greater than 1. So you can send more than 1 symbol per second and get the payment for that job. The only question now is, how do you do this? And the answer is encoding. Let's say that instead of the current codes for our states, you change them to these ones that have 2 properties. Firstly, they make more probable messages have shorter lengths and less probable ones longer. And secondly, no message is a prefix of another one. So there is only one way to decode the sequence of messages. The codes are called Huffman codes. I won't go into much detail on how to generate them, because there is already a magnificent video by Reducible on the subject, that I will link in the description for those interested. The expected length of our message will be the sum over all possible states that multiplies the probability of sending that state by the length of the message required to send it. We go over all of the states and calculate what is the average length of our message after changing the encoding. And it turns out that our average length is now 1.87, which is very close to our entropy that described the amount of information, meaning that we are very close to perfect compression. To calculate the rate at which we can send our data now, we divide the capacity by our new message length, giving us a rate greater than 1 message per second. And just like that, you managed to solve the problem that a lot of people would claim to be impossible. With that, we come to the end of another episode. Hopefully, you can now see how useful information theory can be, and you appreciate the beauty of the fundamental theorem for the noiseless channel.